Alright, let's learn another very valuable tool for our toolbox, the conservation of linear momentum. And there's also going to be an angular momentum law, and we'll deal with that later. But this is just like the conservation of energy, except we're only dealing with the term momentum. Sorry, not rho. Momentum is the mass times the velocity, and these are both vector quantities, right? We learned about impulse too, and how impulse can change the momentum of a system. We said that the impulse is equal to the change in momentum. And if we say that there are no impulses applied, no external forces, we can say that the momentum of the system is constant. So from that we get another conservation law. We say that the momentum initially is equal to the momentum final for a particle or for a system. You can imagine just a particle with some mass and some velocity v. It's traveling along. If no forces act on it, we get a Newton's first law case. It just keeps moving on with a constant velocity, and its mass doesn't change either. Therefore, at some time later, at some time 2, we are just in a different location with the same velocity and the same mass. So it was conserved, no forces were applied. And this gives us a valuable tool because we can extend this to the systems. We can say the summation of all the momentum initially is equal to the summation of all the momentum finally. And we'll see this mainly with two objects colliding, but it can be a whole system. But basically, before is equal to after. What do I mean? I mean, let's say we have two objects colliding, and they're going to be something simple like a hockey puck for now, or a disc. Oh man. If I could get another disc going. There we go. And they could have different masses, so we'll call this M1 and this M2. And some collision just took place. And I'll talk more about this, but there's this line of impact. They hit this line of impact right here. And let's say one had some initial velocity of 1 and the other one is coming in this way. Well, we can say that the momentum before the collision is equal to the momentum after. So we'll assume that they're equal enough in mass so that this one also will rebound back. And this one would also rebound back. I recommend doing full subscripts on this for the particle number and the initial and final state. Real easy to lose it in the algebra. So we can say that the mass times the velocity, or its momentum, m1 v1 initial, plus whatever this one has for its momentum, m2 v2 initial. They're going to collide, they're going to impact each other, and whatever the momentum was before is going to equal the momentum after. So we get m1 v1 final plus m2 v2 final. And this was in one direction, but we can extend this to vectors, meaning that we would do M1 V1 initial in the x direction, M2 V2 initial in the x, and so on, and also for the y direction. So momentum is a vector, unlike energy, which we weren't able to break up energy, right? We're just concerned about the displacement and the speeds. This we can actually get two sets of equations out of it, plus dot dot dot. M1 V1 initial in the y direction plus M2 V2 initial in the y direction. So we get up to 3, if it's in 3 dimensions, we get 3 equations that we can use. And that would be what if this one had some initial velocity coming in like this? Maybe this one has an initial velocity coming in like this. That means the momentum is along the same direction. It's in the same direction of the velocity vector. And we can break it up into x and y components. So this has some velocity in the y direction, some velocity in the x. Just like this has some velocity in the x direction and some velocity in the y. So if we know the angle, we can figure out how to break it into components, and it allows us to use a very fundamental relationship, just the mass times the velocity, to look at big systems and solve for how fast they're going after collisions. We're going to extend this and add some rules to it and talk about different types of collisions, but for now, that is momentum.